Good morning. So what we're going to do is, first of all today, in the first part, is to continue, or rather sort of finish off our ideas about what substitution and what substitutability is. So what we saw last time, if we look here at the lecture note sheet, is there was a definition of what it meant for a term to be substitutable for a variable in a formula. So it's kind of, I would think of this as quite unproblematic, apart from the bite of the definition is all here in the last clause. So I'll say that a term is substitutable for a variable in a formula if the formula is atomic. It's substitutable in a negation if it's substitutable for the thing being negated. And likewise for this propositional connective, it's substitutable for this implication if it's substitutable both for the antecedent and the consequent. So the last clause here is where things happen. So we say that the term is substitutable for VK in this formula, and the formula is itself a universal formula. It's for all Vn psi. It's universally quantified formula, I should say. So it has to be substitutable for VK in the subsidiary formula, psi here. But there were these various rules that we had to make sure that we didn't have untoward consequences. So if Vn happens to be one of the free variables of the term that's being substituted in, we could get a clash. We'd bind a variable of the term by this outside quantifier. Okay, so we say if that is in danger of happening, then actually Vk is not one of the free variables of phi. So though we're defining T is substitutable for Vk in phi, it might be Vk is not one of the free variables of phi. There might be any Vk that's in phi may already be quantified by another 4 Vk inside there. So if there's a danger of a clash, then Vk is not one of the free variables, and then nothing should happen. That's the idea here. Right? So this, of course, builds in some kinds of defaults, right? I mean, maybe Vk appears nowhere in the formula phi here, in which case all of this amounts to nothing happening at all, right? We do have substitutability. Right? So we have some kind of defaults built in, but there are some peculiarities. Right? Right? So there's a warning down here. Just because a variable is not free in a formula, it does not mean in general that a term is substitutable for it. And there are two examples below. Right? So again, just to think about what this means is, we might have a variable which occurs in a formula, but it's bound by a quantifier. Right? But it doesn't mean, according to this definition, the term is officially substitutable in square quotes for that formula, for that variable in the formula. But when Vk is a free variable, right, then the definition works perfectly well. Now on the next page is another rather formal looking subfunction right here. So the subfunction just says what happens when you actually do the substitutions. Right? So I've written it out in this rather kind of formal, rather programming language-like way. Sub is defined in terms of relations or function symbols applied to things that we've already applied sub to. Right? But in fact, this is just what Charles Morgan was writing as, this is the result. When I apply the subfunction, the result of, for a formula or term x, of substituting t for vk. So I read the subfunction here from left to right. I substitute this for this in that. Right? So t for vk in x. There's an alternative way of writing this here. So I would say officially this is an induction on the numerical complexity of the terms and formulae. Right? So let's just see how this is going to work. So a kind of base case, a term, the result of substituting t for vk in vn, well, it depends whether k equals n or not. If k equals n, the upshot is t. I put t for vk, and vk then is the result, t. On the other hand, if k is different from n, nothing happens because k doesn't appear in vn. If I've got a relation here of various terms, and this is why it's an inductive definition, I assume I know what the subfunction is applied to these terms, t1 up to tn, so I apply it. And I say the result of substituting in t for vk in this is the relation R of those substituted things. And the same for functions. This is for R's in the vocabulary of relations of the language and F's for functions. And I think if one were to substitute in T for VK in a constant symbol, right, the result is just the constant symbol here. Constant symbols are in a way just zero-y function symbols. So this is for Cn, the constant symbol collection. So that deals with substitution into terms. Now we do functions, substitution into formulae. So here's an atomic formula. It's a equation. I substitute T for Vk in this equation. So I substitute in T for Vk in the terms on either side. And I get this resulting equation. And then propositional connectives are unsurprising. A T for Vk in this negated formula is the negation of the substitution into the formula. And likewise for implications. I just substitute into here and then into here, put an arrow between them. And then down here, we've got, I substitute T for Vk in this formula for all Vn psi. Now the upshot here is if k equals n, nothing happens. If k is different from n, then we do the substitution T for Vk in the underlying formula psi. And then put for all Vn there at the front. So in terms of this other description, it's for all Vn psi with T for Vk here. Now there's an important note here. Right? This subfunction is somewhat independent of that previous definition here. Right? So the sum function just mechanically does these substitutions, but it doesn't pay any attention to this final clause. It just does some substitution. It's just a mechanical process. So we'll see that, I mean, whether T is actually substitutable for Vk in phi is not really taken care of here. It just says this is what we do when we do the substitution. It doesn't pay attention to whether T actually is substitutable for Vk and phi according to this definition. It just steams ahead and does it. But on the other hand, right, if T is substitutable, for VK, right? In the formula, right? As per the other definition, then the subfunction does the right thing. Well, there's quite a lot of examples here to look at. So basic thing here. I substitute Vn into Vk. I substitute Vn for Vk in Vk. This gives me Vn. Now we're going to look at substituting in this function f of v0, v1 here for v2 in various formulae phi. Okay, so we'll start with this atomic formula. This is relation between v1 and v2. So when I substitute in this function for v2 in phi, this kind of happens unproblematically. According to the definition here, I have to substitute it in for the various terms first, and put it inside R. So I substitute for the various terms, here just v1 and v2. So I substitute the function for v2 in, well, v1, and then I substitute again for v2 in v2. Well, substituting this for v2 in v1, there's no v2 here inside v1, right? So nothing happens, right? It's this clause up here. So I get v1 here. But now something does happen. I substitute f for v2 in v2, and I end up with f. If I look at an implication, again, it's kind of fairly automatic. I look at the substitution for the whole implication. Well, I just do the substitution for the antecedent, and I do the substitution for the consequent there, here. So I just look at that. Here, I'm putting in the function for v2 in here. So this should end up as r of v0 with the function. Here, v2 is not appearing in this formula. So actually nothing happens. And now the more interesting bits when we've got this for all quantified formula in the front. So these are universal formulae. Again, so I just look doggedly back at the definition here, and I see what happens. Right? Well, in the first case, I'm substituting in the function for v2 in this formula here. Right? So, well, I just go ahead and do it. Right? That's what the clause, this last line, does here. And nothing problematic happens because the free variables of the function are not v3. On the other hand, I want to substitute phi in I want to substitute the function for v2 here. But this is the quantifier on the outside. So the clause here says nothing happens. So I just end up with phi. And now I do a more problematic substitution. I substitute in the function for v2 in phi, right? Okay, so phi is itself for all v1, r v1, v2, and f contains v1 as a variable. Right? Nevertheless, the clause here just says you just go ahead and do it. I put for all v1 on the outside, and I substitute it into the underlying formula here. And that's what I've done. We have r of v1, and I put in the function for v2 here in place of, I put in the function in place of v2 here. Right? So I've got r of v1 and now the function. Right? And now I have committed a clash because this variable here has now got bound by this quantifier up here at the front. And I've got an unintentional sort of binding of this here. So this is an example of what I was saying. The subfunction does the substitutions without prejudice as to whether the t actually is substitutable for vk. It doesn't perform a check first to check whether it is actually substitutable. It just goes ahead and does it anyway. But if we know from some other prior reason that the term is substitutable, the right thing happens here. So again, one of the points is that everything that we do here is entirely algorithmic, right? Checking for substitutability and actually doing the substitutions is all something that we could write down a computer program